astronomy, you study the cosmos, what's the difference? And it turns out that there really is a difference, because as you might know, astrophysics actually, or astronomy as a field actually is one of the oldest disciplines that exists, that became physics, right? And in a way that makes sense, because if you were just a person, who just sort of was there like 10,000 years ago, you probably wouldn't learn about anything about atoms or anything like this. You wouldn't even be able to probe the materials of the properties of materials very readily. But what you could do is just wait until it's nighttime and look at the sky. Now, cosmology is sort of concerned about something even bigger, right? And you might say, what's bigger than space? And so, really, it's in a sense, it's an even more old discipline, but not in the sense that you might think, right? So, cosmology deals with questions which are sort of on the grandest of scales. First one is a question like, where did we come from? Where did the universe come from? And then what will happen next? Or the universe. And so this particular bit is important, right? Cosmology is really the study of the universe. And when I say the universe, I don't mean like in the astrophysical sense, like planets, stars, galaxies, things inside the universe. If you're an astrophysicist, you might see a galaxy and say, that's the Milky Way. But a cosmologist would look at a galaxy and say, well, that's just another galaxy out of the infinite number of other galaxies that are in the universe, right? They're concerned about the large-scale evolution of the universe at very large scales. Like how the universe was at very early times, how it will be many cosmological epochs from now, right? Not so much like the nitty-gritty details that sort of concern astrophysicists. So this is sort of the sense in which this field is different. You can see why this would be like an older discipline, but the kind of cosmology that we're going to be talking about is not just cosmology, it's actually formally called physical cosmology. Physical as in physics. And you might say, well, that seems like kind of obvious, like we're talking about physics here. But the thing is, these sorts of questions, as you might imagine, are not questions that people would stray away from asking, even if they knew nothing about physics, right? And so, anytime you hear a culture with its own religion or its own folk story about how the universe was created, that's also referred to as a cosmology, right? But the difference, humbly, I pose that the difference between those kinds of cosmologies and these kinds of cosmologies is that we have a chance of knowing the right answer. So one big question that we can ask. Has the universe always been here, and is it infinite in extent? Well, that's an interesting question that I think most of you guys superficially know the answer to. But I want to pose you something called Olber's paradox, which is going to sound kind of boring at first, but it's very, very strange if you think about it, especially if you were sort of back in the day. When you look into the sky, you see stars. But suppose the universe is so big, so let's just say we think it's infinite. So if we look in a direction, right, if the universe truly is infinite, right, then eventually some arbitrarily far away there should be a star. Any direction we look, there should be a star there. It might be really far away, but because the universe is infinite, there has to be a star there. And if the universe is infinitely old, that light should have traveled to us. Right? Now when you look at the sky, it's very clear that, you do see some stars, but there are many directions you can look where it's dark. Right? And so that's sort of the puzzle of Olber's paradox. If the universe has always been here, and it's infinite in extent, how come the universe doesn't light up? The night sky. Why is the night sky dark? Right. And I'll give you a few minutes to talk about this with your neighbors. Maybe you already know the answer to this. But this seems like a puzzle, right? Why is the night sky dark if the universe is so big, right, and very old? So I'll give you a few minutes to talk about that. All right, anyone have an answer to this? Yes? No? Anyone have any idea why Olber's paradox is not a paradox, how it gets resolved? Yes?
Because some stars we can't really see because of different temperatures.
That's possible, but if the universe is infinitely old, recall, I don't know if this was explicitly mentioned, but like entropy increases in the universe, right? And what that really means is that like if you have two like blocks that are at different temperatures and you touch them together, you can imagine that after a long time that they become the same temperature, right? So if the universe is infinitely old, that means it has had an infinite amount of time to come to equilibrium. And so everything should glow in, like the same brightness, right? Yeah, so not quite, right? I think one sort of puzzle, one sort of solution people try to pose is that there's sort of like, maybe there's a gas cloud that's like in the way and you can't see the stars. But eventually, after a very long time, the gas cloud would feel so much radiation that it actually would also burn as bright as a star. Or like it would glow as bright as a star. So it's not quite the resolution, but definitely thought of before. Any others?
So the light can only travel so fast.
That's right, yeah.
Where we're able to see.
Right, for sure. So one thing that you should be thinking of is, well, we assume these ideas. So naturally, it's right to assume that one of these might be wrong. And if you know that this first one is wrong, the universe hasn't always been here. In fact, it started in a hot Big Bang. Which is sort of like a singularity point at the beginning of the universe. In other words, the universe has sort of a beginning point, which is sort of not intuitive, right? Like it doesn't really make sense. Like you look at the sky, it doesn't seem to evolve, right? Why would you expect it to have come from some time, right? In fact, Einstein actually pushed back against this idea, but we'll talk about this in a little bit. So this is, yeah. And so the resolution to Olber's paradox is that the universe is not infinitely old. Yeah. But there are some other observations you can make about the universe, right? And these are maybe not observations that make sense at first, but I'm going to pose them as things that I assert to be true. These two concepts of homogeneity, and isotropy. You guys, have you guys heard of this before in any context? What does it mean? Does anyone know?
Oh, we talked about it last week.
Oh, you did. Okay.
Yeah, go ahead.
Yeah, so homogeneity is essentially like the universe looks the same everywhere you are. Okay? And isotropy means it looks the same every direction you're looking. Now these sound like very similar concepts. They're kind of subtly different, right? But the important thing is that at large scales, the universe is basically like uniform. And I might say that doesn't really make any sense. In astrophysics, it's never the case, pretty much, right? Like this room is not uniform. There are places of very low density, the air. Then there are places of high density, no offense. Even when you look at the solar system, right? Like most of the solar system is empty, right? Save for like like planets and the star, like in the sun and like asteroids and stuff like this. And then on very grand scales, you have like galaxies and then spaces with less galaxy in them, right? And so it seems sort of strange that I would assert like these two things to be true. Like that at a very large scale, you really can't see any detail, it sort of smooths out. And what I'm saying basically is the universe is like not a fractal in that sense. Like if you zoom out, like it's just flipped. Okay. Yeah. And so it seems like a very strange thing to assert, but I pose first of all that this simplifies the math a lot. But second of all, it actually turns out to be true. So even before people knew this was true, they're like, we can't really do anything else, so we'll just assume it. But we checked and it looks like it is true. So yes, I guess. And so one thing you should know is that the universe expands. And so a lot of the hardware cosmology is to discuss how it is that the universe expands, what it affects its expansion, why it expands the way that it does. And so the way that you can think about this is sort of like this. Suppose like, yeah, let me think how to do this. Get a chair, can't reach. So suppose I have like some galaxies here, and like here. And so like let's say this is some distance, right? Then later on, after a little while, you'll have like this galaxy, if you're like, it might still be here, then this one's sort of stretched out. This distance is stretched out by a little bit. And this distance is also stretched out by a little bit. Right? You see what I'm saying? Like, let's say like this is like, I don't know, like 2 times. I didn't draw it very well. Like 2 times multiplication, right? Now, if you were like living in this galaxy right here, you would like look at these galaxies and you would be like, hey, those are going away from me, right? And it's tempting to say, well, if you look everywhere, every galaxy is going away from you, right? Because if you sort of imagine a galaxy here, it sort of like gets stretched out this direction. But if you think about it, no. It's sort of like anyone at any galaxy would see that the universe is sort of expanding like this, uniformly. So really, you're not at a privileged place, but it is in fact the case that the Big Bang sort of happens everywhere. It doesn't happen in one place. That's a common misconception, by the way. And so, what's critically important here, right? Yeah, if you think about it, is that if you were making observations of these, recall that there's something called radial velocity that can tell you how fast things are receding from you. This galaxy here would actually look like it's receding farther away, faster than this one. And to see this, you notice that even though the universe has expanded sort of evenly, this galaxy has moved less than this one. Can you see that?
So we talked about redshift last lecture. This is an elaboration on that concept. Yeah.
And so like this is sort of like a concept that sort of blew people's minds, right? The farther away something is, the faster it appears to be going. Seems to be interesting. Question?
Yeah, like how is it that like when they're moving apart, the galaxy themselves aren't like expanding too?
That's a very good question. So it turns out
people aren't expanding.
that's a good question. Yes. So that's a very common and very insightful question. But basically, at small scales, like gravity is actually able to hold things together, but at large scales, it can't hold things apart.
So the greater the distance.
At cosmological distances, where like this assumption is true, right? Recall that this isn't true at all scales, but it's true at large scales. So in large scales, like this approximately holds. Yeah, and so I wrote 2 times here, right? This number is called the scale factor. And what do I mean by the scale factor? Well, let's set the scale factor equals to 1 today. Let's say I had like a length that's like this long, like today. Now, like many billions of years ago, it might have been this long, right? Because the universe is expanding. So this length corresponds to a length of this, right? The scale factor is basically what fraction, like the length, would correspond to. If that makes any sense, right? So for example, like if this is the length today, and like tomorrow the universe expands a little bit, like twice as much, it basically describes how much the universe has expanded, right? Normalized to today. So today it's 1, just by definition. Does that make any sense? Like, I hope that's okay. And so, one thing that's important, because we are nominally physicists, so we like to think about reality, is we would like to ask, how do we learn about the universe? And so, as you might have remembered, we really learn most of our information about the universe from light, right? Light. And even though this is cosmology and like a little bit more specific than astrophysics, it really is the same idea, right? Like that's really the only thing that can get to us, besides gravitational waves and neutrinos and stuff like this. But we won't worry about that right now. But one thing that's interesting is that from this perspective up there, you can see that things that are farther away appear to be receding faster. What that practically means is that they look redder. Because as you recall, like as something is receding away from you, it has a Doppler effect that causes the light from it to appear redder. That's sort of one way to think about it. Arguably, it's not the best way to think about it, but let's just go with that for now. This kind of reddening is called redshift. And it's given the letter Z. But here's the thing, right? As was mentioned before, things that are farther away, like if something's farther away, it means that light has had to travel longer to get to us, right? And even though the universe is expanding, it is still true that something's farther away definitely took longer to get to us. So practically speaking, when you look like at very far away observations, you're looking at those objects as they were like a long time ago. Now, if you're looking at the center of the galaxy, that might be like a few tens of thousands of years, which is like not too long. But if you're looking at like cosmological scales, that could be like a million years, a billion years, billions of years, right? And so practically speaking, when you look at very far away things, you're really looking back in time. But because things that are farther away also recede faster, they're also more reddened. So that's the same thing as redshift, roughly, right? And finally, because the universe is expanding, knowing this also in principle tells you the size of the universe at that time, right? Like this is not an equality, but these like sort of correspond to each other. What does that mean? Well, what that really means is that if you ever read something written by a cosmologist, like it turns out that like this is the number we actually measure, and all of this stuff like sort of depends on our model of the universe. And so if you ask a cosmologist how long ago did something happen, they'll say something like, oh, z is equal to 3. They'll tell you the redshift like as like a measure of like time or distance or something like this, because this is what they measure, right? And so really redshift is the number that people start to use. And so, yeah. So one might ask a question also. What is it that the universe like actually looks like? And so that brings us to a discussion of curvature. And we did discuss this in GR a little bit. But recall that if you have a triangle on flat space, then the angles add up to 180 degrees, right? You remember this? This is sort of like 8th grade geometry a little bit, right? Like if you add up all the angles in a triangle, they definitely add up to 100 degrees if you're on a flat piece of paper. But is this actually true in our universe? Like we did learn in general relativity that in fact, space-time doesn't have to be flat, it could be curved. In fact, it could be curved uniformly everywhere. That doesn't violate isotropy or homogeneity at all. So that begs the question, what is the curvature of the universe? And really, there are only three things that this could be, right? I mean, it could be positively curved, or it could be negatively curved, or it could be flat. Now we've sort of talked about what flat means, right? This means like the angles add up to 180 degrees. If it's positively curved, that means they add up to more. What that really means is it's like sort of like a spherical geometry, like the Earth, in a way, except like three-dimensional. So if you tried to draw like a triangle, then the angles would add up to more than 180. Similarly, negatives would be less, so this would sort of be like a potato chip geometry, or like a saddle. But either way, these, like, if the universe were sort of curved but on a very large scale, we actually wouldn't be able to tell the difference. So we actually don't technically know which one this is. But the thing is that we can actually like do some measurements, and I won't really go over what those are, but it turns out that you can actually show the universe is flat. So last time we said the universe was flat, and everyone's like, what? You think the Earth is flat? No. But it is true that as far as we can tell, the universe is flat. It turns out this is sort of strange. But we'll talk about that coming up. But then it bears to keep in mind this concept of curvature, right? Because it does play a bit of a role in cosmology, right? And in particular, the way that cosmologists today frame this problem of curvature is very interesting. Okay, so let's talk about this different thing. You guys remember what a metric is? You probably remember from your homework, right? I gave you some like really weird looking one. What is a metric? Does anyone remember? Does anyone remember what lecture it's from? Yes.
Is it the 7 units, the 3 direction?
Kind of. It's sorry, can you elaborate?
The 3 axes?
Yeah, kind of.
X is Y, axis is Z.
That's from the special relativity.
Yeah, special and general relativity. So recall in special relativity, it was sort of just always -1, 1, 1, 1. But in general relativity, it actually depends on the mass and energy of the universe, or stuff in the universe. Turns out this is no different. It turns out there is a different metric that describes the universe on a very large scale. This is called the Friedman-Robinson-Lemaitre-Walker metric. But people sometimes leave off or add other people to this. But then people conventionally call it this, so I'm just going to do that. So something that I want you to know about this, first of all, like other metrics that we've shown you, this does in fact have 3 terms, right? And second of all, there is a time-like term, and it doesn't look the way that you expect. And third of all, there is a section here which sort of depends on time. What this is really saying, like this number, actually, this is the same A as before, right? What it's saying is basically that over time, like lengths actually like sort of increase like their value in the metric, right? So in other words, the universe expands, right? And so this is sort of like what comes out of general relativity, right? And it turns out this is actually only the metric for flat space, and you can see this because today A is 1, and so if you set A equals to 1, then this just becomes the special relativistic metric, right? But if it's curved, there are actually like sort of different changes that you would have to make. But roughly speaking, it looks something like this. It has like this A here. It's interesting. What does this do? One question that you might ask, because I sort of asserted that the way that the universe is curved and how it evolves depends on what's in it. And my question is basically, how is it like that stuff in the universe affects how A evolves, right? like by looking at stuff in the universe, can I predict how fast it will expand? The answer is yes, actually. And so, this is the Hubble constant here. This is the Hubble parameter. The Hubble constant is basically how fast the universe is expanding today. That's something we can measure. The Hubble parameter is actually how fast the universe is expanding at any time. Turns out that it's kind of bad because the Hubble constant is not a constant. Okay? It actually changes over time, it changes day to day. It just doesn't change fast enough for you to actually notice that. But in any rate, it does change. And so we would like an equation to tell us how that number changes. How fast does that expansion rate change? And so we would like to figure that out. Okay. Well, what kinds of stuff could be in the universe? Anyone? Anything? Mass? What kind of stuff has mass? Matter. Yeah, that's right. Yes, but there's not that much of it in the universe as it turns out. That's a mystery, by the way. We don't know why. Yes. Sorry. Stuff that could be in the universe. Great. So we got this excellent suggestion. Matter. Yes. And yes, that's correct. And indeed, let me pose a question. So, if I have some box, some three-dimensional box, okay, and I have some particles in it, 3 particles, okay. Suppose at some later time, the box sort of this is today. And then later in time, it's A equals 2. So the box, each side of the box has doubled in length. The box is sort of 8 times bigger. And then these 3 particles are sort of farther apart. So I would like to ask, how does the density of the box change? The number of density of the box change as the number of particles. Sorry, as the scale factor goes up. If the scale factor doubles, what does the density become? Does that make sense as a question? Sorry. Does anyone know the answer? Pardon? Decreases by how much? 1/8. 1/8. It becomes 1/8, right? You can see this because you can split up this box into sort of 8 equally sized cubes, all of which were the same size as this one, but it has the same number of particles in it. So the volume went up by 8 times, but the number of particles is the same. And so, so basically what this means is matter, which I'm going to call, I'm going to say the fraction of the energy of the universe that's in matter is going to be called omega m. I'm going to say that this is goes down as the 3rd power of A. And what that means is if the scale factor is A, so if it's 3, then the energy density will have gone down as 3 to the 3, which is 27 times. Does that make sense? What about light, radiation? Let's draw it over here. Suppose I have a box, and it has some photons in it. And the photons have some energy in this box, some energy density. So later, as the universe expands, by twice, let's say, these photons are still here. How has the energy density of the photons gone down? Does anyone have an idea? Any guesses? 1/8. How about you? 1/8. So that's a tempting thought. certainly it is true that the photons are sort of like the same number of photons. And so like you would be tempted to say, well, there's the same number of photons, so they're going down by 1/8 because the box has increased the same amount. But you want to be careful, right? Because actually light gets redshifted. Right? And it turns out that as light gets redshifted, it actually turns out that the energy density in the box goes down even faster. Because not only does the box get bigger, and so this, like, you know, the volume got bigger, but each individual photon gets stretched out, so its energy is being taken away. Right? So actually it turns out that light will go down as a to the minus 4, which is to say it goes down faster than matter. Right? Finally, can you think of the last one? Does anyone know? I don't know if you guys can guess. Dark energy. Why is it called dark energy? Because we don't know what it is. Which is kind of sad. People use the letter lambda. I don't know if you remember this letter lambda. It showed up in general relativity as a number that Einstein put in because he wanted the universe to not crunch down. But he called it his biggest blunder. And it turns out that actually it kind of was because, you know, he sort of thought that the universe, you know, should be sort of stable forever. That definitely isn't the case. But it wasn't really a mistake in the sense that people actually had to go back and dig it up once they realized, well, we need an explanation for why the universe is expanding faster and faster. Anyone have, I don't think this is obvious at all, but does anyone have a guess as to how this falls off with time?
Do you want to explain, like, more vaguely what dark energy is? Because that might help.
Yes. Okay. So dark energy is essentially this mysterious energy density that causes the universe to accelerate its expansion. It's kind of weird. If you think that's strange, well, it is. It turns out. So one of the things that our physics department has won a Nobel Prize for actually was Saul Perlmutter and John C. Mather, right? Is that right? No, that's not.
No.
I don't think so.
Saul Perlmutter and Adam Rees.
That might be, yeah. So what they did was they actually discovered the universe was not only expanding, but it was actually accelerating. So to imagine how weird of a discovery that is. It's like if you threw like this in the air, you're like, okay, well it goes up, and gravity pulls it back down. And the universe has gravity, so you'd think that would happen too. But actually what they had observed is basically they had thrown a marker in the air, and then it continued to go up faster and faster and faster forever. And going faster the farther up it was, right? And so we're like, what is that? That doesn't make any sense. We did the math and we checked, and it says that should not happen. But it does. So does anyone have any idea how this falls down? Any guesses?
Would it go up?
It doesn't go up. Or it might go up,
It's
but
related to your question, actually. The question about why humans don't like expand over time. Remember, Nicholas's answer to that was over small scales, the expansion is very small.
So
over large scales, the expansion is very large.
the thing is, some people, like, there are models where it does go up, but people don't think this is the case, actually. Anyone have any other guesses? Yes?
It stays constant.
That is correct. As far as we can tell, it does not change. Can you imagine how strange this is? The universe expands, right? And sort of everything in the universe goes down in this way that makes kind of like sense. And then there's just this stuff that just exists. And no matter how much the universe expands, this stuff is just always there. Right? So imagine after a very long time, everything is just going to be dark energy, right? Yeah.
So when you say it's constant, it's the energy density that's constant, or is it?
It's the energy density. Yeah, it's the density. So I want to be kind of careful. Like I've been sort of sloppy here. Like you should kind of, what you should really be writing is like not this symbol exactly. Like this is a schematic, right? Really like this number actually goes up because these numbers go down, and this is the fraction of the stuff in the universe. But just if you think of it as a density, then it doesn't change, right? It just is there. It just, from your perspective, it's like there's more of it being generated every day. That's what it looks like, which is really bizarre if you think about it. So let me write out this equation. 0. So this is the radiation today. A to the minus 4 plus 0 and a to the minus 3 plus and then a to the 0, so nothing. And then there's another one thing I left out was these are supposed to be like fractions that add up to 1, right? But there's actually, like, if you think about it, I could pick numbers for which this doesn't add up to 1. And like, that should be okay, I guess. And it turns out that there actually is another component, which is sort of like people sort of refer to as an energy density, which is curvature. Right. And so essentially, here's the statement. The statement is that, oh, by the way, curvature falls off as a to the minus 2. So it falls off basically slower than anything else. So in a curved universe without dark energy, the entire universe would just get more and more curved over time. But because dark energy exists, dark energy can dominate and sort of suppress the curvature. But anyway, as you can see, right, here we're getting sort of a first glimpse at how the stuff in the universe affects the dynamics of the universe, right? Depending on how much stuff you have, like, that determines like the curvature that you have in your universe. Does that make sense? Like, which turns out to be quite important, right? Because if you think about it, we sort of related sort of this geometric property of the universe to the stuff that's in it. Furthermore, we have now this like handy equation that sort of tells us how it is that the universe expands over time. This is called the Friedmann equation in this form. It's one of the prettier versions of it. Okay. And so let me just give a little bit of intuition for that, what that looks like. If you have a universe which has like radiation in it, it will sort of go up like this. So it will go up and it will actually end up slowing down, right? Because if you think about it, if you look from here, if you just imagine all of these were like not here, just think about this term, then this number goes down over time. So the Hubble parameter goes down. And it turns out that it does in fact expand forever in this kind of situation, but it will just sort of keep expanding like slower and slower. And it turns out that it's also the same for like if you just had matter and stuff like that, right? But it's not the same for if you had dark energy. This is sort of matter, radiation only. So this is sort of like A, this is like time. So dark energy is lambda. It goes up exponentially, right? And furthermore, if you look at this equation, you can sort of see what things take over at the beginning and what things take over at the end. Right? So at the beginning of the universe, as you can see, radiation sort of dominates everything, right? And then at the end, like dark energy will dominate everything. Now, if dark energy didn't exist, then curvature would dominate everything. And then there's a puzzle, because if there's even a little bit of curvature in the universe, then like why don't we observe it today? Because it would have grown like massively, right? So that's a puzzle. That's strange. I think we'll get to that at some point. Yeah. Okay. But that's a puzzle that I'll postpone for a little bit of time. But I want you to keep it in mind. Why is our universe not curved? One of the forefront questions of physics that people think they have an answer for. So I want to go over a brief history of the universe, just as an outline, in case you wanted to know. There's a common misconception that sort of the universe expands constantly, and so you can take the Hubble constant, do 1 over the Hubble constant, and get the age of the universe. Turns out that actually works really, really well, even though that's not true, because it just sort of coincidentally works out that way. But it turns out the universe doesn't expand equally. I'll show you what it sort of does expand like. So it sort of expands like this. So it sort of has a big bang, and it sort of expands because, like, at the beginning of the universe, radiation and matter sort of take over. So the universe sort of looks like it has only radiation and matter in it. And at some point in the past, it sort of turns over like that. And then at this point, around this point, is where dark energy takes over. So with that in mind, let's talk about what the history of the universe is. So first, some weird stuff happens. Sorry about that. We'll talk about it right at the end of the lecture, what weird stuff happens here. But then, after you sort of grant me that transgression, the universe is sort of radiation dominated. Which, like I said, you can see because radiation sort of falls off the fastest, which means sort of, if you go back in time, it's sort of growing the fastest. So at the beginning of the universe, everything is like radiation. Then like seconds to minutes later, like the universe cools enough to form nuclei. So like atoms, basically. Like the not atoms exactly, but the nuclei of atoms, sort of the nucleus, right? And this actually turns out to be a very important period of time. Right? You might think like seconds to minutes, like sure that might be very significant on that period of time because the universe doesn't know what a second is, it hasn't had any. But it turns out that this period of time is critically important. And how long this period of time is very important because it turns out, may not be something you know, but neutrons, if they're not in the nucleus, actually decay in like 10 minutes. Like they have a half-life around 10 minutes. They're stable inside of an atom, but not outside of an atom. And so at the beginning of the universe, you basically had all of these free neutrons floating around in space. And it's too hot for them to sort of form atoms. So for that period of time, they're like decaying, right? And then once the universe cools down, then they can like find a proton, like make an atom, and then be stable. But before that, they're sort of just stuck there, right? And it turns out that the reason why this time is important is because it tells you basically how many neutrons there can be in the universe, right? Roughly speaking. I'm not saying they can't be generated or destroyed, but being honest, this is like really sets what that number is. And so this period of time is called Big Bang nucleosynthesis. Big Bang nucleosynthesis. Because it's sort of like the creation of nuclei, so nucleosynthesis during the Big Bang. And then about 500,000 years later, so we're really jumping now. Matter takes over. By the way, I forgot to mention, anyone have a guess for what fractions of the universe these components make up today? Matter? I'm counting dark matter here, by the way. So matter, not dark matter, is about 5%. Matter is like about a fourth. Okay. Radiation is like 0. It's very, very small, actually. Because most of the universe is not this. And then dark energy is about 3/4. Which as one of our professors, Eugene, likes to say, is about 50-50. Yeah.
Cosmologists approximate everything.
But as you can see, if you add these together, it's 1. So there's no room for curvature in this picture. But anyway, that digression aside, matter takes over at this time. So matter is now 50% of the universe. And then, 100,000 years in, one of the first, this is sort of a new development, but one of the first molecules actually formed. You're not going to believe this. I don't know if you do chemistry. It was actually a helium and a hydrogen, so it's helium hydride. And if you do chemistry, you might realize, like, what the hell, that shouldn't exist. That doesn't make any sense. I think it's an ion or something. But in any case, this is sort of like, apparently people have discovered that this exists. And it's really weird. I recently read actually today, while looking through some research pages, that somebody is doing work on like solid hydrogen gas apparently exists in the universe or something, like in the form of snowflakes or whatever. Not quite this, but I think that's how they pitched it. Anyway, it's pretty insane. And then this is an important bit. So this one's actually super, super interesting to cosmologists today because we can actually look at this period of time. And so I haven't really given you a full picture of what the universe looks like at this time, but this is what's called recombination, which is sort of dumb. Like cosmologists point this out all the time. This is why it's a wonder why they don't change the name. But recombination implies that there was a combination, which there wasn't. This is the first time, right? Recombination basically means this is the time at which the universe is cool enough that electrons can start sticking to atoms and creating actual atoms. Because recall, before this, you sort of had a bunch of nuclei floating around, but the electrons were sort of floating around too. And because they were floating around, that meant that any light that was going around couldn't travel very far, because it would just bounce off of an electron and then go another direction, bounce off, go another direction. And the universe wasn't see-through, it was opaque, right? Until this point in time. What does that mean for us? What that means is if you look back in time, you literally can't like see past this, right? Like you sort of see like sort of this wall, and then you can't see past it. This is like sort of the farthest we can go. Maybe we can use gravitational waves if people are thinking about that. But until we get there, this is as far back as we can see. And it turns out that this wall that you see is called the cosmic microwave background, footprint of the universe. And then the universe becomes dark. Dark ages. And then the universe, at 10 billion years, so right now we're at 13.7, is when dark energy takes over. Okay. So the fate of the universe is something we can ask about. And I'm going to give you two answers that people think are wrong. There's either, so if lambda is actually increasing, which is a guess, people actually think this could be true, but probably isn't. But if it does increase, it turns out that, as I think Nikhil pointed out, or someone pointed out, that the universe sort of just keeps expanding more and more, dark energy gets stronger and stronger, the actual energy density goes up, and then literally, planets start to get ripped apart, and then like people start to get ripped apart, and then atoms start to get ripped apart. And this is called the Big Rip. I didn't make this up. This was before the time of memes. And if it turns out this is too weak, then we get the big crunch, which basically means that at some point in time, like the universe sort of gets overcome by gravity, crunches back in, and then like we're dead. Big crunch. But the one we think will happen is lambda is constant. And this causes the big freeze. Which basically means the universe sort of, as stars sort of go out, the universe becomes dark. And then sort of things all go to thermal equilibrium. The universe is expanding so fast that photons can't even catch up to each other anymore, right? And then you just sort of have a bunch of photons floating around in the universe. Your black holes might evaporate, your protons will evaporate depending on whether or not you believe that can happen. But basically the universe sort of freezes over, and it's in thermal equilibrium, as you learn in statistical mechanics, and then nothing can happen ever again.
Entropy always increases.
Yeah, so that's pretty depressing, I would say. But that's sort of what we're reckoning with. But before then, and this is like a very long time from now, like infathomably long, before this time, and before like all these fuel sources go out, we still have a bit of prospect. So we should really try and keep our planet from being put in a microwave. Yeah. Let's talk about this footprint of the universe that I was sort of discussing before, sort of preempting. As I said, this hails from about 300,000 years ago. And as you can tell, I'm not a cosmologist because I told you the number, right? But a cosmologist would tell you it's about z of 1,000. And what this means actually is that if you have if there's some light emitted, it would have been stretched out by 1,000 times by this time. Right? So this is quite significant, right? And it turns out it's very interesting how this thing was discovered. So it turns out that one of the first theorists to actually think about this kind of thing was James Peebles, right? Jim Peebles, actually. And he was one of the winners of the Nobel Prize. So it turns out last week, we got to hear about exoplanets, and so Shishir and Shashank are very happy about this. And then this time we get to hear about cosmology. So this is sort of the wheelhouse of Jim Peoples, right?
Just to clarify, it's 300,000 years not ago after the Big Bang.
Sorry, this is, yeah, you're right. I sort of just wrote it out of habit. No, this is like very early in the universe, not 300,000 years ago. Thanks for that. Yeah, and so it turned out that basically at this place called Bell Labs, right? There are these two people named Wilson and Penzias. And this happened in 1964, so when my dad was born, actually. Basically, there are these like huge radio dishes that people were using, right? These two guys, and they sort of like found that if you pointed your radio dish anywhere in the sky, you would hear like this like fuzz, like you would just see like something everywhere, like the sky was lit up in microwaves. They're like, what the hell is going on? It doesn't make any sense. So what they did was they're like, you know, maybe we screwed this thing up. So they went in there, they cleaned out all the pigeon poop out of the detector. They're like, it didn't work. What do we do now? And they tried a whole bunch of things, and then some theorists came and were like, yeah, this is probably actually real. You saw something. And in fact, they won a Nobel Prize for this. So it's great that they came along. And indeed, so this thing actually exists. Like we've seen this, we've imaged this. And I'll show you some pictures in a second if we get to it. But there's some things that you should know about it. So they find CMB. First of all, the CMB emits like a black body. So if you remember what the black body spectrum looks like, it basically emits like as if it's a perfect black body. So in fact, the temperature of that black body is 2.73 Kelvin. That's about 3 degrees above absolute zero. That's the first fact. So it's quite cold. One thing you should know is that the universe sort of cools down like over time, right? So it turns out that it cools down inversely proportionally to, the temperature is inversely proportional to the scale factor, A. Which means that the universe is very hot at early times, very cold today. So today it's 2.73 Kelvin, right? And the light from that time got stretched to be microwave length, which is very long. Second, it's very uniform. It's super smooth, right? Like, in fact, there are bumps in it, but they're very small bumps, right? By and large, it's extremely smooth. And in fact, it turns out that if you actually do this measurement, you'll find that one side of the sky is like much bluer than the other. It turns out this is actually because we are moving with respect to the cosmic microwave background, and so that one side is blue shifted with respect to the other, which is red shifted. But like we know where this comes from, so we can just subtract this off. And so like mostly uniform, right? But not completely uniform. Okay. Turns out like there are fluctuations. And like you might like in temperature, right? You might ask how big these fluctuations are, and I'm going to say that they're about 1 in 100,000. So very, very small fluctuations, but they're actually extremely important. And there's something called the power spectrum, which you can find from this, but I'll discuss this when we actually show this on the screen. But it turns out that, just to preempt this, these fluctuations are sort of the seed of structures in the universe, right? They might seem like very small fluctuations, but because the universe sort of blew them up to big size, right? They sort of become like the place where like galaxies form and stuff like that, right? This is like what causes the structure in our universe to form. It seeds it. Okay. Yeah, we still have quite a bit of time. It's good. Okay. All right. So that's the cosmic microwave background. I suppose we also have time to talk about dark matter. Okay. I think maybe we should save that for discussion. 20 minutes. I think we can do this. Okay. So let's go back to this question about what. Yes.
Okay, still like name checks. The big freeze is also called the HITA.
Yes. Yeah.
And cosmic microwave background, is that also the cosmic background radiation?
Yeah, probably. Or
Yeah.
cosmic microwave background radiation. Yeah. Yeah, probably. There's also a cosmic infrared background background, I think. But that's from like dust or something. So who
Oh,
cares?
yeah, the fork stuff.
Yeah, something like that. But I want to pose you this question again because it really should be bothering you. Why is the universe not curved? So recall what I said before. As long as there's no dark energy, right? And like if you think about it, dark energy hasn't been important for most of the universe. Only been important for the last 3 billion years or so. That really isn't that long of a time to think about it. Although it's a very long time ago. The question is, if dark energy wasn't there to sort of stop curvature from taking over the universe, that means if there was any curvature, even a tiny bit of curvature at the beginning of the universe, it would have blown up significantly and we would definitely notice it. But the thing is, we do our measurements and we find out that that doesn't matter. We're like, what's up with that? Look at this, right? So why is the universe not curved? And this is sort of related, by the way, let me write down this number, because people have actually calculated this, or like measured this. Omega k, which we recall is sort of the amount of curvature energy density in the universe, roughly speaking, will be 0.000 plus or minus 0.005. So, you know, pretty close to 0, right, as far as we can tell. We can check some more, people do, but by and large, we're pretty sure that it's 0 within however much we can measure. So this sort of brings us to this first question, the flatness problem. Okay. And the flatness problem is basically this: why is the universe flat? And of course, with all of the implications that I sort of posed, right? And this is sort of a really big question because if you think about it, it's sort of like as if you were sort of like had a ball, you sort of rolled it along a razor for like miles because the universe is really old, and then somehow like got to the end and didn't fall off. That's insane, right? Even if there was some tiny perturbation in like which way the ball was going, it would fall off immediately, right? Very quickly. So why is it that somehow like today, like we just have to believe that there was exactly 0 curvature in the universe? It's strange. Yeah, so that's one question. Another question is called the horizon problem, which is basically like, it's a little, so one thing I maybe should show you, put in a bit, is that the cosmic microwave background sort of looks like a bunch of like spots. Like if you subtract off like the part that's all the same, then it sort of has like these blotches on it. And like, the question is basically something to the effect of, well, these blotches, you can sort of estimate how far apart the edges of these blotches are. Because you figure that, well, these blotches sort of are like regions where like the temperature is approximately similar. So that means stuff over there has had time to come to thermal equilibrium, right? But if you actually do this calculation, you'll find that these blotches are way too big for light to have sort of crossed from one side to the other, right? In other words, how did this side of the actually there's let me rephrase this. There's actually a more stark example of this. If you look in 2 different directions of the sky, right, you'll see like the CMB this way and the CMB that way. I told you that these were basically the same temperature, right? But if you think about it, like this, like how could this side of the universe have the same temperature as this side if it took like light like so long to get to us? Like how would it have time to tell this part of the universe to be the same temperature, right? Like there seems to be no way that these 2 sides of the universe could have come to thermal equilibrium. So why constant T? How does the universe know to be at the same? There's a different problem which is sort of strange. Arguably not a problem, but maybe it is a problem. But it's definitely mentioned a lot. Maybe it would sort of make more sense if we had Russell's discussion, but unfortunately we didn't because of the outage. But essentially the idea is that there are a lot of grand unified theories that are trying to explain sort of the concordance of quantum mechanics and relativity, right? General relativity, more precisely. Turns out a lot of those theories predict magnetic monopoles. Now, targeting back to E and M, I'm just going to write down these equations again. I'm just going to write these down. The other ones don't matter. So recall that, like, there are no such things as magnetic charges as far as we can tell. We've never seen one of those before. But it turns out that some theories actually predict that, in fact, such a thing does exist, right? Right? And so then the question becomes, well, we expect at the beginning of the universe for a bunch of magnetic monopoles to be created. And then the question is, where are they? Where did these go? Now this is arguably not a problem because we haven't ever confirmed that those theories are true, but cosmologists insist that it's a problem, so I apparently have to write it down. And all of these are solved by this one hypothesis, which has not been proven, but which has a very interesting backstory. Does anyone have any questions so far? I mean, this is sort of the beginner's guide to the universe, and we're literally talking about the universe. So, if there is ever a time that you would be confused, it would be now, I think.
Question?
Yes?
Like by flat, what do you mean by that exactly?
Yes. I mean, yeah, so I neglected to mention this before. Basically, let's say you had like a ruler, okay, and like, you sort of like set it on the ground, you had a different ruler and a different ruler, right? And you know the rulers are like straight. Then if you like put them like in a triangle and measure the angles, they should add up to 180 degrees, right? Do you agree with me? Now the thing is, like, the Earth is not flat, right? Despite what it says on the problem set. So the question is, why don't you detect the curvature of the Earth? Well, it's because the Earth is so big that you just can't be sensitive to that curvature, right? But if you made your triangle big enough, eventually you would notice that the angles don't add to 180 degrees, right?
So if you go all the way from the North Pole down to the equator, then go along the equator, and then back up to the North Pole, that's a triangle. But you can do that, and the angles will add, like each angle will be 90 degrees.
Yeah.
90 plus 90 plus 90 is
Yeah, 277. All right. You see, so the thing is though that you can like do like things which are equivalent to this measurement, but for very large scales, as large as we can tell, and those will give you 180 degrees. Right. Whereas if there was any sort of deviation from 180 degrees, I claim that sort of curvature would have forced the universe to be even more curved over time. Does that make sense? Yeah. Any other questions? Before I tell you the thing that cosmologists think is the truth? Yes?
Maybe this pretty big question, but like I know the universe is like flat on the scale of the universe, but like what's the height of the universe?
Oh, I see. Okay, so it's an interesting question. So turns out that even though you sort of have a picture of like a mat which is sort of like bent in some way or something like this, it turns out that it's not like bending into something. It just has an intrinsic curvature. So it turns out that it really doesn't make too much sense to say like how high or low it is. There is something called the radius of curvature though, which sort of describes sort of how much the universe is curved. But it turns out this is like maybe like a different notion, just sort of as a number that describes that.
we're really referring to if you were to shine a laser all the way into like the depths of the universe. Would the lines remain straight over long scales?
Another way to put this is if you shine two lasers next to each other, like perfectly parallel, would they eventually cross? Would they eventually go farther away from each other? Or they eventually keep going next to each other? And if you're in a flat universe, then they would like just stay parallel forever. If you're in a positively curved spherical universe, then they would collide. And if you're in a negatively curved universe, they would just go apart. Right? Does that make sense? Okay, cool. So the solution to this, which you might have heard, is called inflation. Now the important thing to know is that inflation does not mean the Big Bang. It doesn't mean the inflation of the universe. It doesn't mean that's expansion, right? This is not that. So whenever you read about the word inflation, either it means this, which I'm about to tell you, or the person who's writing doesn't understand what they're talking about, right? So inflation is basically this idea, like between about, and this is a very much about, 1 times 10 to the minus 36 to 1 times 10 to the minus 34 seconds, like the universe grew about a 1 times 10 to the 15 times, right? So like 1 with like 15 zeros after it, at least. But it could be like 1 times 10 to the 27, which is like what people are currently saying, or more. Really, there's no upper limit. There's sort of just a lower limit, right? Like this is all happening like almost instantaneously, right? Right as the universe begins, right? And as you can see, this is a little bit different than what we're talking about, right? Because if that happened today, we would all be screwed. So I guess we're fortunate that this is not the case. So the question is, how does this solve our problems? Well, it does solve the horizon problem, believe it or not. No, well, let's go to the problem first. You can sort of think of of inflation sort of as like dark energy, but like on steroids, kind of. Like, in the sense that it basically has the effect of flattening out the universe, right? It sort of expands the universe, it sort of dominates everything in terms of the expansion for that period of time. Sort of any curvature that's there flattens out so much, like, because see how much the universe would be expanding in this theory? That the universe is expanding so much that like any curvature you have is like been so suppressed that it wouldn't have been able to grow enough for you to see it. Yes?
Does it grow by a factor of that much, or?
A factor of that much. Like literally like multiply your universe by that much. Like A is like this many times smaller before inflation. That's the statement. Any other questions? Yeah. So it solves because it flattens out the universe, basically. So I'm not here to claim that it flattens out the universe completely, but I'm claiming that it flattens it out enough so that you can't see it anymore, and that it wouldn't have had a chance to grow. Then there's the horizon problem. And that gets solved because if the universe was so much smaller back then, that means that these 2 points, which are other sides of the universe, would have had time to actually come to thermal equilibrium. And then after inflation, they're really far apart, and we wonder why, they sort of are are able to be at thermal equilibrium. Really, in this picture, there's no surprise, right? Because we're like, okay, well, like in inflation, they're actually almost at the same place. Maybe it's okay. Finally, the monopole problem. Is if you had a bunch of monopoles in the universe, after inflation, they would sort of be so dilute that you would just never see one, ever. Because there just wouldn't be, like, there'd just be so few that you would just never find one, ever. And so these are sort of, this is basically sort of the foundation of inflation. Now, the story of inflation is a little bit weird because it was thought up by someone named Alan Guth, and people in cosmology tend to like to think that this is true. And so it turns out that if you look at the cosmic microwave background, you can look at not just the actual temperature, but you can look at the polarization of the light, so there's sort of the direction that it's propagating at you. We might have talked about this before, I believe. And it turns out that inflation is predicted to cause these sort of patterns called B modes in the polarization. So it turns out that your polarization sort of like, you can think of it as like a line on the sky, and your polarization will sort of look like a spiral, like this. If you ever see cosmology like papers or like cosmology articles, they'll sometimes talk about this in the cosmic microwave background. And in 2014, there's someone there was some group that actually claimed to have detected these B modes by looking at the sky. So they popped their champagne bottle. Because if you think about it, no one had ever proven this to be true. So they're like, we figured this thing out like like, we're gonna go to Stockholm, win a Nobel Prize. Like, if somebody, by the way, if somebody like found this out, they would like win a Nobel Prize like, next year, like guaranteed or something, right? And then like it turned out that they just saw dust, or like roughly speaking, they just forgot to subtract off dust in the correct way, and so then like they were completely humiliated because they gave a press conference and everything. So don't do that. And so the guy actually like almost worked for him as a high schooler, but he actually wrote a paper which was like, no, he wrote a book called like Losing the Nobel Prize. Like that. So what a legacy. But you know they're still looking, so one day they might find it and then it'll work out. But there's one thing which people like to invoke inflation for even more, which is arguably one of the most compelling reasons why people want it to be true. And it's called large-scale structure. So one thing I didn't mention, I hope we can get to because we have 8 minutes. I think it's okay. We sort of return back to the beginning of the lecture when I asserted that the universe is approximately homogeneous and isotropic at large scales. You might say, I haven't really shown this to be true. I haven't shown any pictures to you, although I hope that I have the time to. At very small scales, you know, there are people, there's like a planet, there's a sun. This doesn't seem very homogeneous to me. And then if you zoom out, you know, you've got like galaxies. It's a galaxy, sorry. Right? And then if you zoom out even more, you've got like galaxy clusters. This doesn't seem very uniform to me. But then if you go out really far, you sort of get like this web equivalent, which looks sort of like the same everywhere. It's like a cosmic web. And like it might be hard to visualize because I'm not a good artist, but turns out that this is what the universe actually looks like on a large scale, and we've checked this. And so it does look, in fact, very homogeneous and stuff. And so that basically it's like a bunch of like little like fiber-looking like trails of matter. And at the intersections of these, you have like galaxy clusters and stuff like this. And the question is, how did these form? Well, one thing you'll learn about next lecture in quantum mechanics is that there are sort of like random fluctuations in the quantum universe, right? And so like in quantum mechanics, sort of you can't really predict what will happen like exactly in many circumstances, and so you have quantum fluctuations. And the statement is that inflation like sort of made this possible. So when the universe is very small, like sort of there are quantum fluctuations that only happen at small scales and at an appreciable level. And then inflation suddenly happens, blows up the universe really big, and then these fluctuations are now massive, like galaxy level, like massive, right? A galaxy cluster level massive. And then so these sort of seed structure in the universe. Turns out dark matter plays a really big role in this, but unfortunately I didn't allocate enough time to talk about it. So we'll relegate it to discussion, even though it's very, very important. We should definitely talk about it. So this is one of the most compelling reasons why inflation is thought to be true. Now, one final note about inflation, this is sort of very much speculation. Recall that there's no proof for inflation right now, besides like sort of all the things that explains. We never actually confirmed this to be true independently, right? There's something called eternal inflation. People sometimes talk about this, is just sort of a digression, because I don't know if there's any way we could ever show this to be true. But the idea is that, well, what if sort of our universe is like in like a little patch like of the greater universe, such that our universe has stopped inflating, but the rest of the universe just inflates always. And so you have like an infinite universe, most of which is undergoing inflation forever, eternal inflation. But there are sort of little bubbles that show up where like randomly, like this bubble just stops inflating because of like the quantum field or whatever, right? And so you basically have all these little bubble universes in this eternally inflating universe. Right? So it's sort of like a model for like a multiverse, right? And so like, you know, people sort of like, some people like Alan Guth and people like that sort of argue for this kind of universe, right? And indeed it's a very elegant picture, right? Basically you have an infinite universe, except you have like these little bubbles, right? That sort of pop out in this like ever-expanding, ever-inflating universe. And you have this very, very interesting picture to visualize. And I'm sure like, you know, Wikipedia will serve you well. So let's try and get this hooked up really quickly. Do you know how to do this? So a few like random things to show you. Oh, great. Oh, that worked, I think. Can you click that?
can shut off the lights too.
Okay. So one thing that happened a while ago, a long while ago, is that basically we had the Hubble Space Telescope. And I don't know if you know this, but telescopes are really hard to get time on. Like you need to write a long proposal and like tell them exactly what you're going to do and what to look at. And then, especially for Hubble, like you better know what you're talking about. And so these people were like, let's just point at this patch of sky that has nothing in it. Like, why would you do that? It doesn't make any sense. And they're like, what if we pointed there for a really long time? Like a really long time. Like so that we could see whatever is there, anything dim. It's like, what the hell are you talking about? Like, you're basically wasting all of our time. So basically, they just saw a dark patch. But then after a while, like sort of, as more and more photons were like hitting the screen, you could see sort of dimmer and dimmer things because you're like sort of watching that patch of the sky for longer and longer. Eventually, you can see these like little dots show up. If you look really close, you can sort of make out some of them are like spiral shaped, some of them are like ball shaped and things like this. And they don't have like diffraction spikes or anything, which are sort of instrumental, but those are sort of characteristic of like stars or things that are close by. Those are galaxies. Every one of those dots you see, maybe some of them are stars. No, I think pretty much every dot you see in this left picture is a galaxy.
There's only one star in that one.
Where is it? Oh, it's this one right here.
Yeah.
No, there are two. There's one up there too.
Okay.
Yeah, but see these things like those, that is a star, but then the other ones are galaxies. Yeah. And then if you look even deeper, so people did this again for some reason, like even smaller. They saw even more. And this is like a very tiny patch of sky. This is like super tiny. I don't even remember how small it is.
I
It's
think
like
you hold like
Pin
a
at
grain of
arm's
sand
length.
at arm's length. Yeah, like a grain of sand at arm's length.
yeah, that's like
About
this.
that area that makes on the sky is the field of the universe.
Of which one actually?
X.
Extra deep.
This one.
Yeah.
Yeah, so this is the bigger one. This is the smaller one. So this is basically showing that like the universe has a lot of galaxies in it. This is called the bullet cluster. Actually, let's not talk about this last time. Next time. No. Damn it. This is sort of a schematic of what the universe looks like. If you want to look at this some more, you can just go outside and look at that thing over there because it's on our wall. This is a picture of the cosmic microwave background. So this is like over the years, like first the Kobe satellite was actually like won the Nobel Prize for George Smoot, who's a professor here, and John C. Mather. That's right. Was it? I thought it was Kobe. Was it?
I think it was a joint Nobel to Kobe and W
Oh,
math
maybe
perhaps or
that's
something.
true. Yeah. Anyway, so you can see that basically sort of over the years they basically mapped the cosmic microwave backgrounds like sort of fluctuations more and more precisely. And today we're using a satellite called Planck. You can see this is what it looks like. So you can see all this weird structure. Bear in mind it looks a lot different, like very structured, but they've subtracted off first of all the entire universe is like one like very similar in temperature. They've subtracted that off, and then they subtracted off the part where one side is redder than the other because we're moving. But after you subtract that off, you can see all of the structure, which we claim sort of seeds the structure that we currently see in the universe. So this is just the untainted picture. This is a picture of what's called this is a graph of what's called the power spectrum. Basically what that means is, like on the left, sorry, so, yeah. On the left you can basically see small scale things, the big scale things, sorry. So this is sort of big blobs, and this is sort of small blobs. The farther right you go, the smaller the blob it is that's being plotted. You can see that sort of at this like size of blob, there are like very many of those. And then like over here there are very few. And then these red points are data. And this green curve is speed. So you can see there are error bars on this. Right. So you can probably see like we pretty much know like how stuff works, especially at these small scales, right? Until you go too far. This is just a map polarization in the CMB, sort of what people were looking at. They're trying to sort of find this circular looking pattern, and I claim that they didn't really find it. This is a real map of the universe. You can see a cosmic web-like structure. And you can see redshift, meaning distance and also time. And then here's an animation. This is a simulation that was done on a supercomputer. I think this one's called Fire or something. I don't remember what it's called. But basically this is a simulation for how large-scale structure evolves in the universe. So you can see it starts off very uniform. And then as the universe goes, you can see Z is marking the time. Then a web-like structure begins to form. Right. And then when Z is 0, that's the present day. So you can see we get this like web-like structure. And you might ask, is that correct? Yes. And we can actually look. And so, yeah, basically, not only have we sort of like linked the stuff in the universe to how the universe evolves, expands over time, we've sort of figured out what will happen to the universe. We've gotten a glimpse of what the universe might have looked like at the very early stages before we could even see anything. And we've sort of come up with a theory that can basically describe where our structure in the universe comes from. And this isn't just like galaxies and stuff. I mean, it is. But like ultimately the structure ends up becoming like you and me, right? Like recall the universe at the beginning looks very smooth, right? So how is it that like structure like you and me, or like your dog, like where did that come from, right? It sort of gives you an answer, like the ultimate answer maybe. Although like you might see that there's like a lot of work that there's still to be done, and so it's a very vibrant field nowadays. So yeah, that's cosmology.
Any questions?
Yeah, any questions?
Expect a lot of questions from this. So if you come up with any questions you want to ask them during discussion, we encourage that as well.
Yeah, so the lecture's over, so you're free to go. But feel free to also stay and tell us how wrong we are.